Hello, welcome back. In this segment, I will show how we can adapt RSA for digital signature using so-called domain hash signature scheme, FDH, full domain hash signature. Is basically take the message that you would like to sign, but before calling the RSA function, apply a special hash function, which is called the function h here. Let me explain the full domain hash signature scheme. The core idea is that before calling the RSA decryption function for signing, we will first apply a special hash function. It's called h. FDH stands for full domain hash as part of the subscript. FDH is there. So we get a random number y. That's the idea behind this special hash function. And then we go ahead and call the RSA decryption function here. As you can see, y power d mod n. We have been talking about that. So how is the verification going to work? The verification gets two things. One is the message and another is the signature. And the S is the signature, you can imagine. Okay, X is the signature, or yes, in the previous presentation, we used yes. This paper uses X. Okay, it doesn't matter. It's just a small change in the notation. And also, since we are talking about change in notation, this particular research paper uses capital N to represent the RSA modulus, although in sometimes we have used small n for RSA modulus, just to be clear. Okay. All right, let's talk about the verify function, which takes the message and the signature. From the signature, it will recover the hash value, right, by applying the RSA encryption, public value E and N. That will give the value y that was actually signed. And now we will apply the hash function on the message m to get another value y prime. And if y and y prime are equal, then we know there is high chance that this is a trustable pair, meaning message is indeed coming from the signer who knows the private key. Otherwise, we return 0. Okay, that's the idea. So we have sign and verify is exactly the same as we talked about, but one small change is that instead of directly signing a message, we apply a special hash function. This hash function is special in the sense that, as you can see here, it takes a variable number of bits as input, but projects it onto the group Z star n. Okay, that means you get an element on the group. Okay, and that is the reason why we call it full domain hash, because we get a full value, not like a SHA function which gives you only a small size, like 160-bit or so. Here we get the size of the output coming from the hash function is same as the size of the RSA modulus. Okay, in terms of bits. That's the idea of this full domain hash signature scheme. Now you can actually reason about why this scheme is better than the raw RSA function that we talked about earlier. So the reason is that suppose an attacker wants to attack this, right? He has to break the hash function. That is the security argument in this context. If the hash function has some special properties, these are the important properties. It must be difficult to say I have a message m cap. It must be difficult to find m. Okay, if this is one important property. Why do we need this property? Let me explain now. Okay, suppose you are an attacker. Okay, and what you're going to do, you take some number s and apply s power e, okay, mod n. Okay, and you will call this, say, as m cap for a moment. Okay, right, m cap. If it was easy to find another message m such that h of m equal to m cap, then you could simply submit yes and m to the verifier, and the verifier will trust you because hash of m is nothing but m cap, which is same as s power e mod n. If you are able to find another message m that collides with m cap from a hash function perspective, then you could easily create a signature forgery, right, without even having the private key. That is the first important property the hash function should have. Okay, another important property is that we talked about in the previous segment, multiplying two ciphertexts or two signatures to produce another signature. That should not be possible if it is difficult to find this property, meaning hash of m is equal to hash of m1, m2. At least this must be true. These two properties must be true for the hash function that we are talking about. Such a hash function is needed for this RSA full domain based signature. Okay, I hope you got the idea why we need a special hash function, not just any hash function. This is the reason I wanted to explain this sign and verify paradigm. First, we take a message that you would like to sign. Instead of signing directly, we will first hash it using a special hash function, and then we do RSA signature using a private, this is a private exponent D. And when we apply the public exponent during the verification, we get the hash function output. And then we take the message, we apply the hash and check whether the output of the hash function is same as the output that we got after we verify the signature. That's the basic idea of the sign and verify using a hash function. Okay, I gave only an informal overview about the security. As long as the function h is secure, meaning it behaves like a random function, it's difficult to predict, given the range, predict the value of the domain, or having this kind of multiplicative property. In general, we are okay. The function h must behave like a random function. That's the reason we call it random oracle in cryptography. Okay. Then the paper goes into the scientific details of proving the theorem, reducing the security to the security of breaking RSA or breaking the hash function and so on. But I will not go into the mathematics of the proof. But at this point, it's enough to show that if we apply a special hash, I must stress that because it's not just regular any hash function, it's a special hash function. In practice, this idea is used with some slight modification. There are some randomness introduced using salt to the message and padding and so on. But at this point, it's good enough that this is the core of the hash-based RSA digital signature algorithm. That's all. Thank you very much for your attention.